Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review what was covered in week 13. So we ended our topic of trigonometry by looking at equations and modeling. So trigonometric equations are similar to linear equations, except you have a sine, cos, or tan. But the strategy is the same. We want to undo everything that's been done to the pronumeral x, and we do things in the opposite order to what they were done. So here, we multiplied x by 2, then we took the sine, then we multiplied by 4, and then subtracted 1. So the first thing I'm going to do is add 1 to both sides. And what you do to one side of the equation, you must do to the other. So it's just like, in the morning, you put on your socks first, then your shoes. At night, you have to take your shoes off first because they were the last thing you put on. And that's what we're doing here. So we add 1 to both sides, we get this. So the next thing we're going to do is undo timesing by 4 by dividing each side by 4. And of course, what you do to one side, you must do to the other. And that leaves us with sine 2x equals a half. Now, to get x by itself here, I need to undo sine by taking the sine inverse. So I have this equation here. Now, this actually has infinitely many solutions because there are infinitely many angles when you take the sine that give you a half. So these kind of questions will give you a range of acceptable values. Here we're told x has to be between 0 and 2 pi, so that should tell you straight away we're dealing with radians. But even if the question asks for solutions in radians, you can work in degrees if you prefer, and that's what I'm going to do. So if I take the sine inverse of a half and put it on my calculator, well, my calculator's in degrees, it will give me the solution 30 degrees. So I hope you know from the unit circle that 150 degrees will also be a solution. Sine of 150 also equals a half. So there are infinitely many solutions to this, but how many of them are between 0 and 2 pi or 0 and 360 degrees? Well, remember from normal sine graphs, we would normally expect sine x equals a half would have 2 solutions between 0 and 360. But for sine 2x, think about what we did in graphing. We're changing the period, so it's not 360 degrees anymore. It's 360 over 2 or 180 degrees. This one would have 2 solutions every 180 degrees. So I would expect 4 solutions between 0 and 360 degrees, or 0 and 2 pi. So what would be other solutions? Well, remember, if you add multiples of 360 to an angle, you don't really change the angle. It has the same sine, cos, or tan value. So 30 plus 360 will be a solution. 150 plus 360 will be a solution. So you might be thinking to yourself, well, hang on, aren't these two outside the range? But we're going to divide by 2. And they will be in the range. See, each of these is not the value of x. Each of these is a value of 2x. So I get 2x equals 30, 2x equals 150, and so on. So my solutions are, if 2x equals 30, x is 15 degrees. If 2x equals 150, x is 75 degrees, and so on. I just divide each of these solutions by 2. So we're not quite done yet. We've come up with 4 solutions between 0 and 360, but we want our answer in radians. So I'm just going to convert each of these solutions to radians by timesing each by pi over 180. And so here we have 4 solutions, all of them between 0 and 2 pi. And as I said before, I expect 4 solutions. All right, how would I do this equation here? Well, this is a bit more tricky because it has a cos and a sine. What we're going to do to solve this is use the identity that tan x equals sine x over cos x. So how does that help with the equation here? What I can do is divide each side of the equation by cos x. So cos x divided by itself is just 1. And then on the other side, I get minus sine x over cos x. So of course, since tan x is sine x over cos x, this will just be minus tan x. So I get 1 equals minus tan x, or minus 1 equals tan x. So again, I want solutions between 0 and 2 pi. So you can figure out the answer in degrees if you like, and then convert to radians. So if I put this in my calculator, I actually get a negative answer. If I put in my calculator tan inverse of -1 and I'm in degrees, it will give me -45 degrees. So that is a solution to this equation, but it's outside the range that we wanted. So how can I find the solution? Well, you can add 360 degrees to this solution, and I get 315 degrees, which is within this range here. So hopefully from the unit circle, you can find the other solution. It will be, because this solution is in the fourth quadrant, it'll be in the second quadrant, because tan is also negative there. So it will be 90 plus 45, which is 135 degrees. So here, because it's not like tan of 2x or 3x, I would just expect the usual two solutions between 0 and 2 pi. So I've got my solutions in degrees. Now I just convert them to radians. And there we have it. I found the two solutions between 0 and 2 pi, so I'm done. Let's now move on to modeling. So there's two types of modeling questions. Firstly, where you'll be given the equation. Secondly, where you have to come up with the equation. So trigonometric modeling is very useful in things that show periodic data, and tide length is one of those. The tide length goes up and down, day after day. That's what I mean by periodic modeling. So the length of tide at a beach would be well modeled by a sine or cosine graph. So if this is the equation that models the tide length at a beach, y in meters, t the number of hours after 12 a.m., we can answer some questions about it. So firstly, what would be the period of this graph? Well, we remember from trigonometric graphs, the period is always 2 pi over b. The pi in front of here should make it clear that we're in radians. So in this case, b is just the number in front of t, the coefficient of t. It's just pi over 12. So if you put this on your calculator, you actually get the answer 24. Now that makes sense. The period is 24 because t's in hours, it's 24 hours. This means the distance between peaks is 24 hours. The tide reaches a maximum every 24 hours. That makes sense. So it would be the maximum and minimum tide length. So when we're doing maximum and minimum, hopefully you remember from the equations of the sine and cosine graph, the maximum is always the midline plus the amplitude, and the minimum is the midline minus the amplitude. The maximum value this function could take is if the sine of all this is equal to 1. So the maximum possible value is 3.2 plus 3.8, which in this case is 7 meters. The minimum value occurs when the sine of all this equals -1. So it would be 3.8 minus 3.2, which is 0.6 meters. So how easy is that? We've answered the questions. Now let's look at some modeling where we don't know the equation. So let's look at this example here. We want to come up with a model of temperature where the maximum 16 degrees at 3 p.m. on a day and 0 degrees at 6 a.m. on that day. So when we say we want to model this, what we really want is a sine or cosine equation of this form that links temperature in y with x. So what I'll do is I will let y equal temperature, but I will let x be the number of hours after 12 a.m., just like I did on the previous slides. So for this, it will only make sense when x is between 0 and 24, because I'm modeling the temperature over 1 day. So what I'm going to do first is draw a graph to help me better understand this situation. So I want the maximum to be 16 degrees. Now 3 p.m. would be 15 hours after 12 a.m. So I want the maximum to be up here. So the minimum occurs at 6 a.m., which is 6 hours after 12 a.m., and I want that to be down here. So I want some sort of graph that goes down here, stops, turns around, goes to its peak, and comes down again. So as I said, I could use a sine or cosine graph here. Remember, they're just phase shifts of each other. What I really need to do is find the values for A, B, C, and D. Now, whether it's a sine or cosine graph, it will have the same values of A, B, and D. So I will find those ones first. I'll do it in the order D, A, B. So D, hopefully you remember, is the midline of this graph. So if the graph has values from 0 to 16, D will be halfway between there at 8. So D is equal to 8. A is the amplitude. It's the distance from the midline to the maximum or midline to the minimum. So in this case, A is also 8. So what about B? Well, remember, B is not the period. The period is 2 pi over B. So what do I want the period to be? Well, this is a little tricky, but the distance between the minimum and the maximum is 9. Remember, for sine and cosine graphs, the period's the distance between peaks, and the low point occurs halfway between peaks. So if this is one peak, this is the bottom, distance of 9. The previous peak must have been 9 before. It's over here at -3. But even though that's outside our range of values, it helps us find the period. I want the distance between peaks to be 18. Double the distance between the low point and the high point. So that means I want 2 pi over B to equal 18. To solve this equation, you can just move this over to the right-hand side. B will be 2 pi over 18, which is, of course, pi on 9. That will guarantee that the period's 18 and that there's 9 hours between the minimum temperature and maximum temperature. So as I said before, A, D, and B will be the same regardless of whether this is a sine or cosine graph. The last thing to find is C, the phase shift. This value will differ if it is a sine graph than if it is a cosine graph. So let's find a value of C for both of these graphs. So the idea in finding C is I want to make sure that the peak occurs here. All of this is really good. It determines that there will be 9 hours between low point and high point. It makes sure that the range of values is 0 to 16, but it doesn't guarantee that the peak will occur at 3 p.m. So C is going to be used to determine that. So remember, for a cosine graph, its peak is at 0. Y equals cos x, peaks at x equals 0. So if this is a cos graph, I want everything in the brackets to equal 0 at the peak. So when x equals 15, I already know that B was pi on 9, but when x equals 15, I want C to be a value so that this whole thing equals 0, because then I'd be taking cos of 0, and that would be a peak. So, of course, solving this equation, we just want the brackets to equal 0. C will equal -15. That's if it's a cosine graph. What if it's a sine graph? Well, if it's a sine graph, I have to remember that y equals sine x peaks at pi on 2. Sine graphs normally peak at pi on 2. So what I want is when x equals 15, I want this thing in the brackets to equal pi on 2. Because then I would be taking sine of pi on 2 when x equals 15. So solving this equation, I'm going to divide each side by pi over 9. And what I actually get is 15 plus C equals 9 over 2. So I simply subtract 15 from both sides, and I get C equals -10.5. So that's the value C has to be if it's a sine graph to guarantee that the peak will be at x equals 15. So I've found two models here. Values of A, B, and D are exactly the same, whether it's a sine or cosine graph. The only difference is the C value. So one of the functions is y equals 8 sine pi on 9 x minus 10.5 plus 8. The other I found is y equals 8 cos pi on 9 x minus 15 plus 8. Both of these are viable trigonometric models that will ensure that this data here occurs on the graph. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.